Today we're talking about ocean circulation, and we're going to start with surface currents. Now, why would you need to know about ocean currents? Well, there's a lot of reasons. The most historic reason is trade routes. This is how early explorers got around. They got around by following the currents of the ocean and using wind and currents to get around the world. So it's not a surprise that Europeans went south first towards Africa and then across the ocean to the Caribbean, up the North American coast, and back along the Northern Ocean. That's the way the ocean currents were flowing. Another reason you might want to know about ocean currents is to figure out where contaminants are going to go. And this is an experiment, a model simulation actually, looking at where the oil from the Gulf Coast spill a couple of summers ago would go and how quickly it would end up in the Atlantic Ocean. And this is a 2-month simulation. Perhaps the most important thing that ocean currents carry is heat. And that is one of the main reasons that we study ocean currents, is to understand the way that heat is moved around the globe. This is the Gulf Stream, and you can see the pattern of color, which is a temperature of the ocean, coming up from Florida and from the equator north along the coast to North Carolina and then out into the Atlantic Ocean. The Gulf Stream moves a lot of heat and has a very significant effect on climate and weather in the North Atlantic. So there's 3 kinds of ocean currents, and surface currents are what we're going to concentrate on today. But I want to briefly back up and talk a little bit about tidal currents. You know about tidal currents if you've been near the beach. They are due to the gravitational attraction of the moon primarily, and they're important locally if you live or work along the coast. You need to be aware of them. They're what make the water go up and down, or the tide come in and out every day. If there is a river nearby, the tidal currents can be really important about how far the tide comes up the river. And so if you live there and you work there, you need to know about it. But they don't have a long-range global effect, so we're not going to go into them in detail. Thermohaline circulation is the subject of the next mini lecture. Now, before we can delve into currents, we really need to understand why they happen. And the Coriolis effect is a really big part of that. The Coriolis effect is the deflection of anything that is moving freely on a rotating globe. And that means all air or water or anything else that is in motion on the globe. And it is a deflection of those freely moving things. In this case, we're talking about water in ocean basins, as a function of the spinning of the globe. Now, which direction is the globe spinning? Well, if you were to look at it from above, it would look like it's spinning counterclockwise. And that's the little arrow I just drew for you on the globe. If you have a hard time remembering that, you can always figure it out for yourself, so don't bother memorizing it. Pretend you're the sun. Imagine the Earth out in front of you is spinning, and you're staring right down at New York, where the sun is already up, but the sun hasn't come up in LA yet. Which way do you have to turn your imaginary globe to make the sun come up in LA a little bit later today? Well, you're going to have to turn it to your right. So that is the direction of spin. The Coriolis effect means that anything that is moving on the globe will be deflected to the right. That means in the northern hemisphere, it's going to be deflected in a clockwise direction, and in the southern hemisphere, in a counterclockwise direction. So what does that do to ocean currents? It forms these very large currents we call gyres, or circular circulation, in ocean basins. And the Pacific being the biggest ocean basin, let's look at that first. If you look in the northern Pacific, you can see that the northern Pacific gyre is rotating clockwise. It's rotating to the right. In the southern ocean, that ocean gyre is rotating in the opposite direction. It's rotating counterclockwise. Now, of course, you can't have two rotating currents going in the same direction adjacent to each other. So sometimes in smaller areas, more confined areas, you'll get smaller currents that seem to be in the opposite direction, like the Alaska current here, which is in the northern hemisphere, but because it's in this confined little area of the ocean in the very north corner near Alaska, you get a counterclockwise current rotating in there. Now, the other thing that really affects these ocean currents are the boundaries, the continental boundaries. So, of course, the current cannot continue to flow forever in one direction because it's going to run up against land and that's going to change the way it goes. And so in the northern Pacific gyre, you see the ocean moving towards the east along the equator and then up along the Asian continent, across the northern part of the Pacific near Alaska, and then down along the west coast. And in the Southern Ocean, the same thing, the boundary currents going north and south along continental boundaries. Now, why do you think that surfers in California wear wetsuits, but North Carolina surfers don't? Let's look at the boundary currents. The California surfers are dealing with water that's coming down from Alaska, where those North Carolina surfers get to enjoy the water that's coming up from Florida. It's much warmer over there. If we look at a more confined ocean basin, you can see that some different kinds of things can happen. Let's look at a couple of areas of close-up from the previous map. We'll start over here near us in the Gulf of Mexico. You can see that the ocean current is coming across the Atlantic Ocean and into the Gulf of Mexico from the south, from the Caribbean. And therefore it sets up a current in the Gulf of Mexico that's clockwise. Not so much because it's in the northern hemisphere as because it's in this confined ocean basin and it's coming in from the south side. And so the clockwise current in the Gulf of Mexico brings water here in Texas that comes up from Mexico. Now, if you look over in the Indian Ocean, you see the opposite happening. The water coming across the Pacific Ocean is entering the Indian Ocean basin from the east, and therefore it's setting up currents in the northern Indian Ocean that are in the opposite direction of what you expect in a northern ocean. They are counterclockwise currents, and that's because the direction that the water is entering the basin sets up that countercurrent. So boundary currents can really be important.